define a recommendation system. Recommendation systems, or recommender engines, are a class of information filtering system which analyze the input data to predict preferences of a user as they might have done for themselves. Unlike information filtering systems, which remove or filter information, recommender engines add or rearrange the information flowing towards the user, which is more relevant to the current context. They existed in the form of our friends and family who used to recommend us things to buy because they understood our choices. These were, and still are, a sort of offline recommender engines. The web is full of online recommender engines, from recommendations related to who to follow on Twitter, to other movies you might enjoy on Netflix, to jobs you may be interested in LinkedIn. Recommender engines are everywhere, and not just on e-commerce platforms. Now that we've understood what a recommendation engine is, let's look at their different types. The first type is user-based recommender engines. They're also termed as user-based collaborative filters in general due to the extensive use of collaborative filters, specifically for such recommender engines. Another type is content-based recommender engines. These engines have the content or items as the central entities. These items are analyzed to extract features. Also, the user profiles are built to map user preferences to the type of items. The engines then use this information to predict items which are similar to the ones the users have liked in the past. Such recommender engines are also known as item-based collaborative filters. The next type is hybrid recommender engines. These systems take the best of both worlds to improve upon the prediction results. The two pure types can be used simultaneously, and then their results can be combined. They can be used for adding collaborative filtering capabilities to content-based systems, or even by unifying both the approaches into a single model. Hybrid recommendation engines are also better at tackling the problems which haunt recommender engines in general. Now let's discuss the issues with recommendation systems. Recommender engines are affected mainly by the two issues in particular, such as the sparsity problem. Recommender engines work upon user preferences or ratings for different items, depending upon the application to predict or recommend products. In the first scenario, when recommending items to such a user is virtually impossible due to the unavailability of information related to his or her preferences. The second scenario is when an item is newly added to the system. The newly added item will not have any ratings by the users. Recommending such an item would be difficult for the recommender systems. Hence, these two scenarios represent what is termed the cold start problem. Very much like the sparsity problem, the cold start problem also plagues collaborative filters. Moving on to collaborative filters. That will be denoted as CF henceforth, and recommender engines in general use certain terms and definitions to formally define and tackle the problem. Collaborative filters are a popular set of algorithms heavily used across applications. These algorithms work on a simple assumption that similar users showcase similar behaviors. The algorithm assumes that the preferences or ratings of the other users in the system can be utilized to provide reasonable predictions for the active user. Neighbor-based collaborative filtering, also known as user-user collaborative filtering or KNN collaborative filtering. The KNN collaborative filter is used based on the core assumption of similar behavior amongst users with similar preferences. This algorithm makes use of similarity measures to predict and recommend items for the active user. The algorithm follows a two-step approach of first computing the predictions, followed by the recommendations. The three main components of this algorithm are discussed next. The first main component is predictions. The first step of KNN-CF is to make use of the ratings matrix, usually denoted as R, to calculate predictions. Since we are concerned about user-user CF, the neighborhood of active user, the user in consideration, denoted as U, is to be taken into account. The most common measure to aggregate preferences is to use the weighted average of n neighboring users. Mathematically, the active user U's predicted preference for item I, denoted as PUI, is given as where UR is the active user's U's mean rating, S of U, U dash is the similarity measure between the active user U and the neighboring user U dash. Another component is recommendations. Once predictions have been done for the active user, a recommendation list can be generated by ordering the items by predicted rank. This recommendation list may further be fine-tuned by applying certain minimal thresholds and other user-specific characteristics, such as preferences for color, size, price sensitivity, and so on. Thus, this step generates a list of probable items which the user is more likely to buy based on his or her personal preferences. Next is similarity. A similarity measure is an important component of our collaborative filtering-based recommender engine algorithm. There are various similarity measures available for use. The most common amongst them is the cosine similarity measure. This approach represents each user as an n-dimensional vector of ratings, and similarity is measured by calculating the cosine distance between two such user vectors. Mathematically, cosine similarity is given as this equation, where vector RU norm 2 and vector RV norm. Starting with the execution, let's first see what is exactly matrix factorization. Matrix factorization refers to the identification of two or more matrices, such that when these matrices are multiplied, we get the original matrix. It can be used to discover latent features between two different kinds of entities. Now that we know about matrix factorization, let's convert the algorithm into code and prepare a recommender engine for the mobile phone ratings input dataset that we discussed earlier. As you can see here, the input dataset is a matrix with each row representing a user's rating for the products mentioned as columns, such as iPhone 4, iPhone 5S, and so on. The ratings range from 1 to 5, with 1 being the lowest and 5 being the highest, along with 0 representing the missing values. To transform our algorithm into working code, we need to compute and complete the few of the tasks. Let's begin with loading and transforming input data into matrix. Representation is simple. As seen earlier, R provides us with easy-to-use utility functions for the same. Here we'll use productrating.csv file. Then we'll enter a line of code to convert columnar data to sparse ratings matrix. Now that we have our data loaded into an R matrix, we proceed and prepare the user latent features matrix X and item latent features matrix Y. We initialize both from uniform distributions using the runIf function. So, first let's get the number of columns in ratings matrix. The result is stored in the rows variable. Similarly, we'll execute for columns using the ncol function. Then we'll set the latent features k as 2. After that, we'll define the user feature matrix X. The same way we'll define item feature matrix Y. The major component is the matrix factorization function itself. Let us split the task into two: calculation of the gradient and subsequently the overall error. For that, we'll add this code snippet. Here, the calculation of the gradient involves the ratings matrix R and the two-factor matrices X and Y, along with the constants alpha and beta. Since we are dealing with matrix manipulations, specifically multiplication, we transpose Y before we begin with any further calculations. This code converts the algorithm discussed previously into R syntax. All variables follow naming conventions similar to the algorithm for ease of understanding. The next part of the algorithm is to calculate the overall error. We again use similar variable names for consistency. As a final piece, we iterate over these calculations multiple times to mitigate the risks of cold start and sparsity. We term the variable controlling multiple starts as epoch. We also terminate the calculations once the overall error drops below a certain threshold. Moreover, as we'd initialized X and Y from uniform distributions, the predicted values would be real numbers. We round the final output before returning the predicted matrix. Note that this is a very simplistic implementation, and a lot of complexity has been kept out for ease of understanding. Hence, this may result in the predicted matrix containing values greater than 5. For the current scenario, it's safe to assume the values above the max scale of 5 are equivalent to 5, and similarly for values less than 0. Let's execute it. Next, we'll set the alpha value to 0.0002, beta value to 0.02, k, that is latent features, to 2, and epoch to 1000. Let's see a sample run of our code with overall error threshold set to 0.001. Once we define epoch, alpha, and beta, we'll define the prediction matrix by entering this code. After that, we'll define column names with C function. Finally, let's print the data off prediction matrix. This code utilizes the functions explained earlier to prepare the recommendation model. The predicted ratings or the output matrix looks like this. Let us do a quick visual inspection to see how good or bad our predictions have been. For that, we'll open the productratings.csv file from the Files tab. Consider users 1 and 3 as our training samples. From the input dataset, we can clearly see that user 1 has given high ratings to iPhones, while user 3 has done the same for Android-based phones. The following side-by-side comparison shows that our algorithm has predicted values close enough to the actual values. Let's see the ratings of user 3. Now that we have our ratings matrix with updated values, we're ready to recommend products to users. It's common sense to show only the products which the user hasn't rated yet. The right set of recommendations will also enable the seller to pitch the products which have high probability of being purchased by the user. Let's consider user 6 as our active user. This user has only rated Nexus 6, OnePlus 1, Nexus 5 and iPhone 4 in that order of rating. That is, Nexus 6 was highly rated, and iPhone 4 was rated the least. Getting a list of the top 2 recommended phones for such a customer using our algorithm would result in Moto X and Moto G. Thus, we built a recommender engine smart enough to recommend the right mobile phones to an Android fanboy and save the world from yet another catastrophe. This simple implementation of a recommender engine using matrix factorization gave us the flavor of how such a system actually works. In order to provide a seamless capability for use in such platforms, we need highly optimized libraries and hardware. For a recommender engine to handle thousands of users simultaneously every second, R has a robust and reliable framework called the Recommender Lab. We'll be using a dataset that contains ratings for 100 items as rated by 5,000 users. The data has been anonymized, and the product names have been replaced by product IDs. The rating scale used is 0 to 5, with 1 being the worst, 5 being the best, and 0 representing unrated items or missing ratings. To build a recommender engine using Recommender Lab for a production-ready system, we'll perform the first step, that is, extract, transform, and analyze. As in case of any data-intensive, particularly machine learning application, the first and foremost step is to get the data, understand or explore it, and then transform it into the format required by the algorithm deemed fit for the current application. For our recommender engine, using the Recommender Lab package, we'll first load the data from a CSV file, that is product rating data.csv, and then explore it using the various R functions. Let's load the library Recommender Lab. Make sure before loading you've installed and stored it in the working directory. Then we'll read the dataset from the CSV file. After that, we'll create rating matrix from data. For exploratory as well as further steps, we need the data to be transformed into the user item ratings matrix format. So we'll enter image function and view the result in the plot tab. The as function utility converts CSV into the required ratings matrix format. The real rating matrix conversion transforms the data into a matrix as shown in the following image. The users are depicted as rows, while the columns represent the products. Ratings are represented using a gradient scale where white represents missing or unrated, while black denotes a rating of 5 or best. Now that we have the data in our environment, let's explore some of its characteristics and see if we can decipher some key patterns. First of all, we'll extract a representative sample from our main dataset by entering this line of code. Then we'll analyze it for average rating score for our user population. For that, we'll get the mean product rating as given by the first user. You can see that we extract a sample of 1,000 users from our dataset for exploration purposes. The mean of product ratings as given by the first row in our user rating sample is 3.74. This tells us that this user hasn't either seen, rated many products, or he usually rates the products pretty low. To get a better idea of how the users rate products, we generate a histogram of item rating distribution. Generated output shows that the distribution peaks around the middle, that is 3. The histogram is shown next. After that, we'll run this block of code to get the distribution of normalized item rating. On executing the code, we can see this histogram that shows that the ratings are normally distributed around the mean, with low counts for products with very high or very low ratings. Finally, we'll check the spread of the number of products rated by the users. We'll prepare a histogram which shows this spread. Great! So, this histogram shows that there are many users who have rated 70 or more products, as well as there are many users who have rated all 100 products. The exploration step helps us get an idea of how our data is. We also get an idea about the way the users generally rate the products and how many products are being rated. Moving on to the second step, that is, model preparation and prediction. We have the data in our R environment, which has been transformed into the ratings matrix format. In this step, we're interested in preparing a recommender engine based on user-based collaborative filtering. We'll be using similar terminology as described in the previous sections. Recommender Lab provides straightforward utilities to learn and prepare a model for building recommender engines. So, we'll prepare our model based on a sample of just 1,000 users. This way we can use this model to predict the missing ratings for the rest of the users in our ratings matrix. Here we'll enter the code to utilize the first 1,000 rows for the learning model. UBCF in this code signifies user-based collaborative filtering. Recommender Lab also provides other algorithms, such as IBCF, or item-based collaborative filtering, PCA, or principal component analysis, and others as well. After preparing the model, we use it to predict the ratings for our 1010th and 1011th users in the system. For that, we'll add this line of code that will predict the list of products which can be recommended to given users. Recommender Lab also requires us to mention the number of items to be recommended to the users. For the current case, we mention 5 as the number of items to be recommended. Now let's show the recommendation in the form of a list. As you can see, it generates 2 lists, one for each of the users. Each element in these lists is a product for recommendation. The model predicted that for user 1010, product 93 should be recommended as the topmost product, followed by 78, and so on. The final step is model evaluation. We've successfully prepared a model and used it for predicting and recommending products to the users in our system. But what do we know about the accuracy of our model? To evaluate the prepared model, Recommender Lab has handy and easy-to-use utilities. Since we need to evaluate our model, we need to split it into training and test datasets. Also, Recommender Lab requires us to mention the number of items to be used for testing. For the current case, we'll use 500 users to prepare an evaluation model. As you can see here, the model will be based on a 90-10 training and testing dataset split, with 15 items used for test sets. Now let's view the evaluation scheme. Then we'll use the evaluation scheme to train our model based on the UBCF algorithm. The prepared model from the training dataset is used to predict ratings for the given items, so we'll use this to perform preform on the test dataset. We'll finally use the method calculate prediction accuracy to calculate the error in predicting the ratings between known and unknown components of the test set. Let's print the error. For our case, we get this as an output. The generated output mentions the values for RMSE, or root mean squared error, MSE, or mean squared error, and MAE, or mean absolute error. For RMSE in particular, the values deviate from the correct values by 1.218. Note that the values might deviate slightly across runs due to various factors, such as sampling, iterations, and so on. This evaluation will make more sense when the outcomes are compared from different CF algorithms. To evaluate UBCF, we'll use IBCF as comparison. Again, we'll perform the same steps. So first, we'll train the model using IBCF. Then predict on test dataset. Enter few lines of code to compare the error using the calculation prediction accuracy utility. Lastly, we'll change the row names with row names function and print the error. The comparative output shows that UBCF outperforms IBCF with lower values of RMSE, MSE and MAE. Similarly, we can use other algorithms available in Recommender Lab to test or evaluate our models. We encourage the user to try out a few more and see which algorithm has the least error in predicted ratings. For that, we'll enter 2 lines of code. Also, calculate prediction accuracy. You can view this as the output. Awesome! Idea of the different types of analytics which broadly encompass the data science domain. We can broadly classify analytics into 4 different types which are descriptive analytics. This is what we use when we have some data to analyze. We start with looking at the different attributes of the data, extract meaningful features, and use statistics and visualizations to understand what has already happened. The main aim of descriptive analytics is to get a broad idea of what kind of data we're dealing with and summarize what's happened in the past. Above almost 80% of all analytics in the businesses today are descriptive. Diagnostic analytics. This is sometimes clubbed together with descriptive analytics. Here, the main objective is to delve deeper into the data to find specific patterns and answer questions such as why did this occur? Usually it involves root cause analysis to come up with the root of why something happened, and what were the main factors involved during its occurrence. Sometimes techniques such as regression modeling help in achieving this. Predictive analytics. This is the final step in any analytics pipeline. Once you've built consistent and stable predictive models with a good flow of clean data for predictions, you can build systems which utilize this and start prescribing actions which you might take to improve your business. Do remember that predictive modeling can only predict what might happen in the future, because all models are probabilistic in nature and nothing is 100% certain. Prescriptive analytics. This is the final step in any analytics pipeline if you're in the stage that you've built consistent predictive models with a good flow of clean data such that you're able to predict what might happen in the future. Then you can build systems which utilize this and start prescribing actions which you might take to improve your business. Do remember that you need working predictive models with good data and an excellent feedback mechanism to achieve this. Most organizations do a lot of descriptive analytics and some amount of predictive analytics. However, it's really difficult to implement prescriptive analytics due to the ever-changing business conditions and data streams and problems associated with that, the most common one being data sanitization issues. What is credit risk? We've been using this term credit risk since the start of this section, and many of you might be wondering exactly what does this mean, even though you might have guessed after reading the previous section. The standard definition of credit risk is the risk of defaulting on a debt which takes place due to the borrower failing to make the required debt payments in time. This risk is taken by the lender, since the lender incurs losses of both the principal amount as well as the interest on it. In our case, we'll be dealing with a bank which acts as the financial organisation, giving out loans to customers who apply for them. Hence, customers who might default on a loan payment would be credit risks for the bank. By analysing customer data and applying machine learning algorithms on it, the bank will be able to predict in advance which customers may be potential credit risks. This will help in risk mitigation and in minimising losses by not giving away loans to customers who could be credit risks for the bank. The first step in our data analysis pipeline is to get the dataset. We'll be using data analysis and machine learning techniques to analyse financial data from a German bank. We've actually cleaned the data and provided meaningful names to the data attributes, and you can check that out by opening the German_credit_dataset.csv file. You can download the data and then load it using the read command. Then check the class of the dataset. It is DataFrame, and it should be DataFrame only. Next, let's get a quick peek at the data. The result shows the first 6 rows of the data. Each column indicates an attribute of the dataset. We'll be focusing on each attribute in more detail. To get detailed information about the dataset and its attributes, you can use the str code snippet. The code will enable you to get a quick look at the total number of data points you're dealing with, which includes the number of records, the number of attributes, and the detailed information about each attribute, including things such as attribute name, type, and some samples of attribute values. Using this, we can get a good idea about the different attributes and their data types, so that we know what transformations to apply onto them, and what statistical methods to use during descriptive analytics. From the output, you can see that our dataset has a total of 1,000 records, where each record deals with data points pertaining to one bank customer. Each record has various data points or attributes describing the data, and we have a total of 21 attributes for each record. The data type and sample values for each attribute are also shown. That's a good start, as when the data you're dealing with will have missing values, which are often represented as NA in R. There are several ways to detect them, and we'll show you a couple of ways next. Note that there are several ways in which you can do this. We first check if the data frame contains NA values. The isNA function is really useful as it helps in finding out if any element has an NA value in the dataset. There's another way of doing the same by using the complete.cases function. This essentially returns a logical vector saying whether the rows are complete and if they have any NA values. You can check if the total records count has decreased compared to the original dataset, as then you'll know that you have some missing values in the dataset. Fortunately, in our case, we do not have any missing values. However, in future, if you're dealing with missing values, there are various ways to deal with that. Some of them include removing the rows with missing values by using functions such as complete.cases or filling them up with a value which could be the most frequent value or the mean, and so on. This is known as missing value imputation, and it depends on the variable attribute and the domain you're dealing with. Hence, we won't be focusing too much on this area. We had mentioned earlier that by default all the attributes of the dataset had been declared as int, which is a numeric type by R. But it's not so in this case, and we have to change that based on the variable semantics and values. If you've taken a basic course on statistics, you might know that actually we deal with 2 types of variables. Numeric variables. The values of these variables carry some mathematical meaning. This means that you can carry out mathematical operations on them, such as addition, subtraction, and so on. Some examples can be a person's age, weight, and so on. Categorical variables. The values of these variables do not have any mathematical significance, and you cannot perform any mathematical operations on them. As you can see, the numeric variables in our dataset include credit.duration.months, credit.amount, and age, and will not need to perform any conversions. However, the remaining 18 variables are all categorical, and will use the utility function to convert their data types. This function will be used on our existing data frame, credit.df, for transforming the variable data types. Next, select variables for data transformation. Here we've selected the 18 attributes. Once this is done, transform the data types. And finally, verify the transformation. Now we can see that the attribute details in the data frame with the transformed data types for the selected categorical variables in the output. You'll notice that out of the 21 variables, attributes of the dataset, 18 of them have been successfully transformed into categorical variables. This brings an end to the data pre-processing step. Before we begin our analysis, we'll be developing some utility functions, which we'll be using to analyze the dataset features. We'll add the various packages that we need. We use paste.cs for getting summary statistics of features. and then use G models for building contingency tables. Next, add the packages grid extra for getting grid layout. And lastly, use ggplot2 for building visualizations respectively. If you do not have them installed, you can use the install.packages command to install them. Now that we have all the required dependencies, we first implement a function to get summary statistics about the numerical variables. If you see, we've made use of the stat.desc and summary functions for getting detailed and condensed summary statistics about the variable. The conventions for independent variables and dependent variables are denoted by indep.var and dep.var in the code segments that follow, and in other functions later on. Next, we build some functions for visualizing the numeric variables. We're doing that by using histograms and density plots to depict the attribute distributions. We'll also use box plots. We've used the qplot function from the ggplot2 package for building the visualizations, which we'll be seeing in action soon. Now we'll be shifting our focus to categorical variables. We start by building a function to get summary statistics of any categorical variable. The function summarizes the categorical variable and talks about how many classes or categories are present in it and some other details such as frequency and proportion. If you remember, we had mentioned earlier that we'll also be depicting the relationship of categorical variables with the class or dependent variable credit.risk. The function will help us achieve the same in any form of contingency tables. Here we just create the contingency table. We next build some functions for depicting visualizations. Here we're visualizing categorical variable distribution using bar charts by using the following function. We'll use mosaic plots to depict visualizations of the previously mentioned contingency tables using the shown function. Now that we have built all the necessary utilities, we'll begin analyzing our data in the next video. Hi, welcome to the section's final video, analysing the dataset. Previously, we built our dataset utilities. We'll carry out detailed analysis and transformations for some of the important features which have lots of significance, especially data features having a large number of classes, so that we can clearly understand data distributions and how they change on transformation of the data. Now we'll attach the data frame so that we can access individual features easily. You can do that using the code snippet. Now we'll be starting our analysis with the dependent variable credit.risk, also known as the class variable in our dataset, which we'll be trying to predict in the next chapter. This code snippet helps us in getting the required summary statistics for this feature. The stats show that the credit.rating has two classes, 1 and 0, and the customers with a credit rating of 1 are creditworthy, and those with a rating of 0 are not creditworthy. Then we get the visual representation of the same. We also observe from the bar chart that the proportion of credit-worthy customers in the bank is significantly high compared to the rest. Next, we'll analyse the account.balance feature. Basically, this attribute indicates the current balance of the current account of the customer. We start with getting these summary statistics. You can see that there are 4 distinct classes for account.balance, and they each have some specific semantics, which we'll be talking about soon. Next, we plot a bar chart for the same. From the output, you can see that there are 4 distinct classes for account.balance, and they each have some semantics. The 4 classes indicate the main semantics or checking account held for at least a year. First class indicates no running bank account. The second class indicates no balance or debt. The third one indicates balance less than 200 DM. The last one indicates balance of greater than 200 DM. The currency DM indicates Deutschmark, the old currency name of Germany. We'll be doing some feature engineering here, and we'll combine classes 3 and 4 together to indicate customers who have a positive balance in their account. We'll do this because the proportion of class 3 is quite small compared to the rest, and we don't want to unnecessarily keep too many classes per feature unless they're critical. To do so, first load the car package for doing this. Install it using the command install.packages car, in case you do not have the package installed. Now we recode the necessary classes. We'll now see the relationship between new.account.balance and credit.rating using a contingency table, as discussed earlier. You can see now how the various classes for account.balance are distributed with regards to credit.rating. An interesting thing to see is that 90% of people with funds in their account are not potential credit risks, which sounds reasonable. Next, visualize it using a mosaic plot. This also shows the same thing. We also performed two statistical tests here, the chi-squared test and Fisher's test, both relevant tests in contingency tables used extensively for hypothesis testing. Going into details of the statistical calculations involved in these tests is out of the scope of this section. I'll put it in a way which is easy to understand. Usually, we start with a null hypothesis, that between the two variables as depicted previously, there exists no association or relationship, as well as an alternative hypothesis that there is a possibility of a relationship or association between the two variables. If the p-value obtained from the test is less than or equal to 0.05, only then can we reject the null hypothesis in favour of the alternative hypothesis. In this case, you can clearly see that both the tests give p-values less than 0.05, which definitely favours the alternative hypothesis, that there is some association between credit.rating and account.balance. These types of tests are extremely useful when we build statistical models. Now we'll look at credit.duration.months, which signifies the duration of the credit in months. This is a numerical variable, and the analysis will be a bit different from the other categorical variables. The values we see are in months, and we get the typical summary statistics for this feature, including the mean, median, and quartiles. We'll now visualize the overall distribution of the values for this feature using both histograms and density plots. The snippet produces the plots. We can clearly observe that this is a multimodal distribution with several peaks. We now visualize the same in the form of box plots, including the one showing associations with credit.rating next. Interestingly, from the plots, we see that the median credit duration for people who have a bad credit rating is higher than those who have a good credit rating. This seems to be plausible if we assume that many customers with long credit durations defaulted on their payments. Moving on to the next variable, previous.credit.payment.status, indicates what is the status of the customer with regards to paying his previous credits. This is a categorical variable, and we get the statistics for it. 0 class indicates hesitant payment. First class indicates problematic running account. Second class indicates no previous credits left. The third one indicates no problem with the current credits at this bank. The last one indicates paid back the previous credits at this bank. We next get the bar plot for the same. We'll be applying the new transformations to this feature, so the new semantics will be: first class will indicate some problems with payment, the second class will indicate all credits paid, and the third one will indicate no problems and credits paid back at this bank only. To do it, we first recode classes and update data frame. Next, obtain the contingency table for the transformed feature. We observe from the table that maximum people who have a good credit rating have paid their previous credits without any problems, and those who do not have a good credit rating had some problem with their payments. Which makes sense. The next feature we'll look at is credit.purpose, which signifies the purpose of the credit amount. This is also a categorical variable, and we get its summary statistics. We observe that there are a staggering 11 classes just for this feature. Next, we plot the bar chart showing the frequency of its various classes as follows. This gives us a bar chart depicting the data distribution. Here, 0 indicates others, 1 indicates new car, 2 indicates used car, 3 indicates furniture items, 4 indicates radio or television, 5 indicates household appliances, 6 indicates repair, 8 indicates vacation, 9 indicates retraining, 10 indicates business. We also observe that several classes have extremely low proportions, and class label 7 doesn't even appear in the dataset. This is exactly why we need to do the feature engineering by grouping some of these classes together, as we did previously. We'll be transforming this feature by combining some of the existing classes and the new semantics after transformation. So now, 1 will be new car, 2 will be used car, 3 will be home-related items, 4 will be others. To do it, we recode the classes and update data frame. The contingency table for the transformed feature is then obtained. Based on the table, we see that the customers who have credit purpose of home-related items or other items seem to have the maximum proportion in the bad credit rating category. The next feature we'll analyse is credit.amount, which basically signifies the amount of credit in DM being asked from the bank by the customer. This is a numerical variable, and forget the summary statistics. We see the normal statistics, such as the average credit amount as 3,271 DM, and the median as around 2,320 DM. We'll now visualize the distribution of the data using a histogram and density plot as follows. This will give us the histogram and density plot for credit.amount. And you can see that it's a right-skewed distribution in the following figure. Next, we'll visualize the data using box plots to see the data distribution and its relationship with credit.rating. This generates the box plots where you can clearly see the right skew in the distribution shown by the numerous dots in the box plots. We also see an interesting insight that the median credit rating was bad for those customers who asked for a higher credit amount, which seems likely, assuming many of them may have failed to make all of the payments required to pay off the credit amount. Now that you have a good idea about how to perform descriptive analysis for categorical and numerical variables, going forward, we'll not be showing outputs of all the different analysis techniques for each feature. Feel free to experiment with the functions we used earlier on the remaining variables to obtain the summary statistics and visualizations. The next feature is savings, which is a categorical variable having the semantics for the 5 class labels as shown. We'll be transforming it into these 4 class labels. As you know, we first recode classes, and update data frame. Now we analyse the relationship between savings and credit.rating using the code for the contingency table. This generates the following contingency table. On observing the table values, it's clear that people with no savings have the maximum proportion among customers who have a bad credit rating, which is not surprising. This number is also high for customers with a good credit rating, since the total number of good credit rating records is also high compared to the total records in bad credit rating. However, we also see that the proportion of people having greater than 1,000 DM and a good credit rating is quite high, in comparison to the proportion of people having both a bad credit rating and greater than 1,000 DM in their savings account. We'll now look at the feature named employment.duration, which is a categorical variable signifying the duration for which customer has been employed until present. This is the semantics for the 5 classes of the feature. We'll be transforming it to these classes. So recode the classes and update the data frame. Now we analyse its relationship using the contingency table. What we observe from the table is that the proportion of customers having none or a significantly low number of years in employment and a bad credit rating is much higher than similar customers having a good credit rating. In the case of employment.duration feature, the value 1 indicates the people who are unemployed or have less than 1 year of employment. The proportion of these people having a bad credit rating is 93 out of 300 people. This gives 31%, which is a lot higher compared to the same metric for the customers having a good credit rating, which is 141 out of 700 customers, or 20%. We now move on to the next feature, named installment.rate, which is a categorical variable with these semantics. There wasn't too much information in the original metadata for this attribute, so there is some ambiguity, but what we assumed is that it indicates the percentage of the customer's salary which was used to pay the credit loan as monthly installments. We won't be doing any transformations here, so we'll directly go to the relationships. We performed the statistical tests for this variable in the code because we weren't really sure if our assumption for its semantics was correct, or whether it could be a significant variable. From the results, we see that both statistical tests yield p-values of greater than 0.05, thus ruling out the null hypothesis in favour of the alternative. This tells us that these two variables do not have a significant association between them, and this feature might not be one to consider when we make feature sets for our predictive models. The next variable we'll analyse is marital.status, which indicates the marital status of the customer, and is a categorical variable. It has 4 classes with these semantics. We'll be transforming them into 3 classes with 3 semantics. We do the same thing for this too. We now observe the relationship between marital.status and credit.rating by building a contingency table. From the following table, we notice that the ratio of single men to married men for customers with a good credit rating is 1 to 2, compared to nearly 1 to 1 for customers with a bad credit rating. Does this mean that maybe more married men tend to pay their credit debts in time? That could be a possibility for this dataset, but do remember that correlation does not imply causation in general. The next feature is guarantor, which signifies if the customer has any further debtors or guarantors. This is a categorical variable with 3 classes having these semantics. We transform them into 2 variable semantics. For the transformation, we use the same method once again. Performing statistical tests on this yield a p-value of 1, which is much greater than 0.05, thus ruling the null hypothesis in favour, and implying that there is probably no association between guarantor and credit.rating. The next feature is residence.duration, which signifies how long the customer has been residing at his current address. This is a categorical variable with these semantics for the 4 classes. We'll not be doing any transformations, and we'll be directly doing statistical tests to see if this feature has any association with credit.rating. From in the previous tip, using functions fisher.test and chi-square.test. Both gives us a p-value of 0.9, which is significantly greater than 0.05, and thus there is no significant relationship between them. We now shift our focus to current.assets, which is a categorical value having the semantics of these 4 classes. We'll not be doing any transformation on this data, and will directly run the same statistical test to check if it has any association with credit.rating. We get a p-value of 0.0003, which is definitely less than 0.05, and thus we can conclude that the alternative hypothesis holds good, that there is some association between the variables. The next variable we'll analyse is age. This is a numerical variable, and we'll get its summary statistics. To view the feature distributions, we'll visualise it using a histogram and density plot. We can observe from the plots that the distribution is a right-skewed distribution, with the majority of customer ages ranging from 25 to 45 years. We'll now observe the relationship between age and credit.rating by visualising it through box plots. The right skew from the plots is clearly distinguishable in the box plots by the cluster of dots we see at the extreme end. The interesting observation we can make from the right plot is that people who have a bad credit rating have a lower median age than people who have a good credit rating. One reason for this association could be that younger people who are still not well settled and employed have failed to repay the credit loans which they had taken from the bank. But once again, this is just an assumption, which we cannot verify unless we look into the full background of each customer. Next, we'll look at the feature Other Credits, which has the semantics of these three classes. This feature indicates if the customer has any other pending credits elsewhere. We'll transform this to two classes with these semantics. We again recode the classes and update the data frame, and then perform statistical tests on the newly transformed feature. As you can see, we get a p-value of 0.0005, which is less than 0.05, and thus favours the alternative hypothesis over the null, indicating that there is some association between this feature and credit.rating, assuming there is no influence from anything else. The next feature, apartment.type, is a categorical variable having these semantics for the three classes. This feature basically signifies the type of apartment in which the customer resides. We'll not be doing any transformation to this variable, and we'll be directly moving on to the statistical tests. As you can see, both the tests give us a p-value of less than 0.05, which signifies that some association is present between the apartment type and credit.rating, assuming no other factors affect it. Now we'll look at the feature bank.credits, which is a categorical variable having these semantics for the four classes. This feature signifies the total number of credit loans taken by the customer from this bank, including the current one. We'll transform this into a binary feature with these semantics for the two classes. We recode the classes and update the data frame. Carrying out statistical tests on this transformed feature gives us a p-value of 0.2, which is much greater than 0.05, and hence we know that the null hypothesis still holds good, that there is no significant association between bank.credits and credit.rating. The next feature is occupation, which obviously signifies the present job of the customer. This is a categorical variable with these semantics for its four classes. We won't be applying any transformations on this feature, since each class is quite distinct in its characteristics. Hence, we'll be moving on directly to analysing the relationship with statistical tests. Both the tests yield a p-value of 0.6, which is definitely greater than 0.05, and the null hypothesis holds good that there is no significant relationship between the two features. We'll now look at the next feature, dependence, which is a categorical variable having these semantics for its two class labels. This feature signifies the total number of people who are dependents for the customer. We'll not be applying any transformations, since it already is a binary variable. Carrying out statistical tests on this feature yields a p-value of 1, which tells us that this feature does not have a significant relationship with credit.rating. Next up is the feature telephone, which is a binary categorical variable which has two classes with these semantics, indicating whether the customer has a telephone. We do not need any further transformations here, since it's a binary variable. So we move on to the statistical tests, which gives us a p-value of 0.3, which is greater than 0.05, ruling the null hypothesis in favour of the alternative, thus indicating that no significant association exists between telephone and credit.rating. The final feature in the dataset is foreign.worker, which is a binary categorical variable having two classes with these semantics, indicating if the customer is a foreign worker. We again do not perform any transformations, since it's already a binary variable with two distinct classes, and move on to the statistical tests. Both the tests give us a p-value of 0.02, which is less than 0.05, which might indicate that this variable has a significant relationship with credit.rating. We've performed a lot of feature engineering using data transformations for several categorical variables, and since we'll be building predictive models on the transformed feature sets, we need to store this dataset separately to disk. To do it, we use the write.csv function. We can load the above file into R directly the next time we start building predictive models, which will be covered in the next section. As you know in the previous section, we had analysed the credit dataset from the German bank and performed several transformations already. We'll be working on that transformed dataset in this section. We had saved the transformed dataset, which you can check out by opening the credit_dataset_final.csv file. We'll be doing all our analysis in R as usual. To load the data in memory, run the code snippet. This loads the dataset into a data frame which can now be readily accessed using the credit.df variable. Next, we'll focus on data transformation and normalization. We'll be using some utility functions to achieve our goal. First, create a function to convert the data types into factors. Next, create a function to scale the function. The functions operate on the data frame to transform the data. For data type transformations, we mainly perform factoring of the categorical variables, where we transform the data type of the categorical features from numeric to factor. There are several numeric variables, which include credit.amount, age, credit.duration, .months, which all have various values, and if you remember, they're all skewed distributions. This has multiple adverse effects, such as induced collinearity, gradients being affected, and models taking longer times to converge. Hence, we'll be using z-score normalization, where each value represented by, let's say, IE, for a feature named E, can be calculated using the formula, where E represents the overall mean, and _E represents the standard deviation from the feature E. Let's perform it. We first normalize the variables, and then scale the features. Next, factorize the categorical variables. There are 18 categorical variables. This is the line to factorize them. Once the pre-processing is complete, we'll split our data into training and test datasets in the ratio 60-40, where 600 tuples will be in the training dataset and 400 tuples will be in the testing dataset. They'll be selected in a random fashion, as shown. The process of feature selection involves ranking variables or features according to their importance by training a predictive model using them and then trying to find out which variables were the most relevant features for that model. While each model often has its own set of important features, for classification, we'll use a random forest model here to try and figure out which variables might be of importance in general for classification-based predictions. We perform feature selection for several reasons, which include removing redundant or irrelevant features without too much information loss, preventing overfitting of models by using too many features, reducing variance of the model which is contributed from excess features, reducing training time and converging time of models, and building simple and easy to interpret models. We'll be using a recursive feature elimination algorithm for feature selection and an evaluation algorithm using a predictive model where we repeatedly construct several machine learning models with different features in different iterations. At each iteration, we keep eliminating irrelevant or redundant features and check the feature subset for which we get maximum accuracy and minimum error. Since this is an iterative process and follows the principle of popular greedy hill climbing algorithm, an exhaustive search with a global optimal outcome is generally not possible. And depending on the starting point, we may end up at local optima with a subset of features, which may be different from the subset of features we obtain in a different run. However, most of the features in the obtained subset will usually be constant if we run it several times using cross-validation. We'll use the random forest algorithm, which we'll explain in detail later on. For now, just remember it's an ensemble learning algorithm that uses several decision trees at each stage in its training process. We'll first load the necessary libraries. Install them in case you do not have them installed. Caret library is used for feature selection, whereas the random forest is used for random forest algorithm. Now we define the utility function for feature selection using recursive feature elimination and random forests for the model evaluation. By default, the code uses cross-validation where the data is split into training and test sets. For each iteration, recursive feature elimination takes place, and the model is trained and tested for accuracy and errors on the test set. The data partitions keep changing randomly for every iteration to prevent overfitting of the model and ultimately give a generalized estimate of how the model will perform in a generic fashion. If you observe, our function runs it for 20 iterations by default. Remember, in our case, we always train on the training data, which is internally partitioned for cross-validation by the function. The variable feature.vars indicate all the independent feature variables that can be accessed in the training dataset using the train.data subsetting, and to access the class.var, which indicates the class variable to be predicted. We subset using a train.data, 1. We now run the algorithm using our defined function on the training data using the code. It may take some time to run, so be patient if you see that R is taking some time to return the results. On viewing the results, you can see that it's found a total of 10 features that were the most important out of the 20, and it's returned the top 5 features by default. You can play around with this result variable even further and see all the variables with their importance by using the var imp_rfe.results command in the R console. The values and importance values may differ for you because the training and test data partitions are done randomly, if you remember, so do not panic if you see different values from the screenshot. However, the top 5 features will usually remain consistent based on our observations. Logistic regression is a type of regression model where the dependent or class variable is not continuous but categorical. Just as in our case, credit rating is a dependent variable with 2 classes. In principle, logistic regression is usually perceived as a special case of the family of generalized linear models. This model functions by trying to find out the relationship between the class variable and the other independent feature variables by estimating probabilities. It uses the logistic or sigmoid function for estimating these probabilities. Logistic regression does not predict classes directly, but the probability of the outcome. For our model, since we're dealing with a binary classification problem, we'll be dealing with binomial logistic regression. First, we load the library dependencies. Then create a file called performance_plot_utils.r for plotting metric results. These are the functions that will be plotted for metric results. We add this file using this line of code. Next, separate the testing feature and class variables. Now we'll train the initial model with all the independent variables. We can view the model details using the summary lr.model command, which shows you the various variables and their importance based on their significance values. You can see that the model automatically performs one-hot encoding of categorical variables, which is basically having a variable for each category in that variable. The variables with stars beside them have p-values less than 0.05 and are therefore significant. Next, we perform predictions on the test data and evaluate the results. On running this, we get a confusion matrix with associated metrics. It's quite interesting to see that we achieved an overall accuracy of 73.75%, which is quite decent, considering this dataset has a majority of good credit rating customers. It is predicting bad credit ratings quite well, which is evident from the specificity of 48%, sensitivity of 84%, which is quite good, NPV is 56%, and PPV is 80%. We'll now try to build another model with some selected features and see how it performs. If you remember, we had some generic features that are important for classification, which we obtained in feature selection. We'll still run feature selection specifically for logistic regression to see feature importance using the code snippet. We get the plot from which we select the top 5 variables to build the next model. As you can see, reading the plot is pretty simple. The greater the importance, the more important the variable is. Feel free to add more variables and build different models using them. Next, we build the model using a similar approach to before and test the model performance on the test data using this code snippet. Then train the initial model with all the independent variables and build it into the model. We'll now view the summary of the model. Next, we perform predictions on the test data and evaluate the results. We get the confusion matrix. However, if you look at the model evaluation results, you'll see that now accuracy has slightly decreased and is now 72.25%. Sensitivity has shot up to 89%, which is excellent. But sadly, this has happened at the cost of specificity, which has gone down to 32%. And you can clearly see that the more bad credit ratings are being predicted as good, which is 80 out of the total of 118 bad credit rating customers in the test data. NPV has gone up to 55%, because fewer positive credit ratings are being misclassified as false negatives because of higher sensitivity. Now comes the question of which model we want to select for predictions. This does not solely depend on the accuracy, but on the domain and business requirements of the problem. If we predict a customer with a bad credit rating, 0, as good, 1, it means we're going to approve the credit loan for the customer, who will end up not paying it, which will cause losses to the bank. However, if we predict a customer with good credit rating, 1, as bad, 0, it means we'll deny him the loan, in which case the bank will neither profit nor will incur any losses. This is much better than incurring huge losses by wrongly predicting bad credit ratings as good. Therefore, we choose our first model as the best one. And now we'll view some metric evaluation plots. We get this plot from the code. Now we add the code for the recall curve. And we get this plot. Next, we run this code to check the AUC. We get the result as 0.76, which is pretty good for a start. The machines belong to the family of supervised learning machine algorithms used for both classification and regression. Considering our binary classification problem, unlike logistic regression, the SVM algorithm will build a model around the training data in such a way that the training data points to belonging to different classes are separated by a clear gap, which is optimized, such that the distance of separation is the maximum. The samples on the margins are typically called the support vectors. The middle of the margin, which separates the two classes, is called the optimal separating hyperplane. Data points on the wrong side of the margin are weighed down to reduce their influence, and this is called the soft margin compared to the hard margins of separation we discussed earlier. SVM classifiers can be simple linear classifiers where the data points can be linearly separated. However, if we're dealing with data consisting of several features, such that a linear separation is not possible directly, then we make use of several kernels to achieve the same, and these form the nonlinear SVM classifiers. You'll be able to visualize how an SVM classifier actually looks much better with the figure from the official documentation for the SVM library in R. From the figure, you can clearly see that we place multiple hyperplanes separating the data points. However, the criterion for choosing the separating hyperplane is such that the distance of separation from the two classes is the maximum, and the support vectors are the representative samples of the two classes as depicted on the margins. Revisiting the issue of nonlinear classifiers, SVM has several kernels which can be used to achieve this besides the regular linear kernel used for linear classification. These include polynomial, radial basis function, RBF, and several others. The main principle behind these nonlinear kernel functions is that even if linear separation is not possible in the original feature space, they enable the separation to happen in a higher dimensional transformed feature space, where we can use a hyperplane to separate the classes. An important thing to remember is the curse of dimensionality that applies here. Since we may end up working with higher dimensional feature spaces, the model generalization error increases, and the predictive power of the model decreases. If we have enough data, it still performs reasonably. We'll be using the RBF kernel, also known as the radial basis function in our model, and for that, two important parameters are cost and gamma. We'll start by loading the necessary dependencies, and then separate feature and class variables. Once this is done, we build the training data, and then build the SVM model using the training data. And the RBF kernel on all the training set features. The properties of the model are generated as from the summary function. Now we use our testing data on this model to make predictions and evaluate the results. This gives us the confusion matrix like we saw in logistic regression, and the details are depicted from the model performance. We observe that the accuracy is 70.75%, sensitivity is 100%, and specificity is 0%, which means that it's a very aggressive model, which just predicts every customer rating as good. This model clearly suffers from the major class classification problem, and we need to improve this. To build a better model, we need some feature selection. We run a feature selection algorithm specifically for SVM to see feature importance. This gives us a plot, and we see that the top 5 important variables are similar to our top 5 best features, except this algorithm ranks age as more important than credit amount. So you can test this by building several models with different features and see which one gives the best results. For us, the features selected from random forests gave a better result. The variable importance plot is depicted as follows. We now build a new SVM model based on the top 5 features that gave us the best results, and evaluate its performance on the test data using the code snippet. The preceding snippet gives us a confusion matrix finally on the test data, and we observe that the overall accuracy has increased to 76.5%. However, the most interesting part is that now our model is able to predict more bad ratings from bad, which can be seen from the confusion matrix. The specificity is now 42% compared to 0% earlier, and correspondingly, the sensitivity has gone down to 91% from 100%, which is still good because now this model is actually useful and profitable. You can see from this that feature selection can indeed be extremely powerful. We'll definitely select this model and move on to model optimization by hyperparameter tuning, using a grid search algorithm, as shown to optimize the cost and gamma parameters. Finally, we print the tuning.results. The best performance is 0.23%. Next, we get the grid search plot. The darkest region shows the parameter values which gave the best performance. We now select the best model and evaluate it once again. On observing the confusion matrix results we obtained from the output, we are henceforth depicting only the metrics which we're tracking. We see that the overall accuracy has increased to 73%, sensitivity to 91%, and specificity to 28%, which is excellent compared to the previous model results. You can see how powerful hyperparameter optimizations can be in predictive modeling. We also plot some evaluation curves. This is similar to what we did earlier. We can see how the predictions are plotted in the evaluation space, and we see that the AUC in this case is around 0.7 from the ROC plot. Let us just check it using the AUC command. We get the result as 0.75. Now, let's say we want to optimize the model based on this ROC plot with the objective of maximizing the AUC. We'll try that now, but first we need to re-encode the values of the categorical variables to include some letters, because R causes some problems when representing column names of factor variables that only have numbers. So basically, if credit.rating has values 0, 1, then it gets transformed to x0 and x1. Ultimately, our categories are still distinct and nothing changes. We transform our data first. Now we build an AUC optimized model using grid search again. You can see the output on the console. Our next step is to perform predictions on the test data and evaluate the confusion matrix. This gives us the results. We now see that accuracy has increased further to 75%, specificity has decreased slightly to 46%, but sensitivity has increased to 87%, which is good. We plot the curves once again. This gives us the plots, the same as we did in our earlier iterations. Now we calculate the AUC value. As you can see that the AUC has changed from 0.7535 earlier to 0.7483, which means the AUC-based optimization algorithm indeed worked, since it's given better performance than the previous model in all aspects we have been tracking. Decision trees are algorithms which again belong to the supervised machine learning algorithms family. They're also used for both classification and regression. Decision trees are mainly used for making decisions that would be most useful in reaching some objective and designing a strategy based on these decisions. At the core, a decision tree is just a flowchart with several nodes and conditional edges. Each non-leaf node represents a conditional test on one of the features, and each edge represents an outcome of the test. Each leaf node represents a class label where predictions are made for the final outcome. Paths from the root to all the leaf nodes gives us all the classification rules. Decision trees are very easy to represent, construct and understand. However, the drawback is that they are very prone to overfitting, and often these models do not generalize well. We'll follow a similar analytic pipeline as before, to build some models based on decision trees. We start with loading the necessary dependencies and test data features. Now we build an initial model with all of the features. We then predict and evaluate the model on the test data. From the output, we see that the model accuracy is around 69%, sensitivity is 100%, which is excellent, but specificity is 0%, which is excellent. We'll now try feature selection to improve the model. We use it to train the model and rank the features by their importance. This gives us the plot showing the importance of different features. If you observe closely, the decision tree does not use all the features in the model construction, and the top 5 features are the same as those we obtained earlier when we talked about feature selection. We now build a model using these features. We now make predictions on the test data and evaluate it. This gives us the confusion matrix with other metrics. You can see now that the overall model accuracy has decreased a bit to 55%. However, we've increased our bad credit rating prediction, where we predict a 99 bad credit rating customers out of 123, which is excellent. Consequently, specificity has jumped to 44%, and sensitivity is down to 80%. But we still classify a substantial number of good credit rating customers as good. Though this model is a bit aggressive, it's a reasonable model because though we deny credit loans to more customers who could default on the payment, we also make sure a reasonable number of good customers get their credit loans approved. The reason we obtained these results is because we've built the model with a parameter prior. If you check the modeling section earlier, this prior basically empowers us to apply weightages to the different classes in the class variable. In our model, we give more importance to the bad credit rating customers. To view the model, we can use this code snippet. To visualize the tree, we use these lines. This gives us the tree, and we can see that, using the priors, the only feature that's being used now out of the 5 features is account.balance, and it's ignored all other features. You can try and optimize the model further by using hyperparameter tuning, by exploring the tune.r part function from the E1071 package. We finish our analysis by plotting some metric evaluation curves. We get this plot. We next calculate the AUC value. We get it as 0.66. We can see the same in our plot. The AUC, which is not the best, but definitely better than the baseline denoted by the red line in the plot. Based on our business requirements, this model is quite fair. Forests, also known as random decision forests, are a machine learning algorithm that comes from the family of ensemble learning algorithms. Random forests are nothing but a collection or ensemble of decision trees, hence the name. The working of the algorithm can be described briefly as follows. At any point in time, each tree in the ensemble of decision trees is built from a bootstrap sample, which is basically sampling with replacement. This sampling is done on the training dataset. During the construction of the decision tree, the split which was earlier being chosen as the best split among all the features is not done anymore. Now the best split is always chosen from a random subset of the features each time. This introduction of randomness into the model increases the bias of the model slightly, but decreases the variance of the model greatly, which prevents the overfitting of models, which is a serious concern in the case of decision trees. Overall, this yields much better performing generalized models. We'll now start our analytics pipeline by loading the necessary dependencies. Next, we'll build the initial training model with all the features. You can view the model details by using the print function. This gives us information about the out-of-bag error, OOBE, which is around 24%, and the confusion matrix, which is calculated on the training data, and also how many variables it's using at each split. Next, we perform predictions using this model on the test data and evaluate them. The output depicts that we get an overall accuracy of 73%, sensitivity of 91%, and specificity of 33%. The initial model yields quite decent results. We can see that a fair amount of bad credit rating customers are classified as bad, and most of the good rating-based customers are rated as good. We'll now build a new model with the top 5 features from the feature selection section, where we use the random forest algorithm itself for getting the best features. This is the code that builds the new model. We now make predictions with this model on the test data and evaluate its performance. This gives us the confusion matrix as the output, with the other essential performance metrics. We get a slightly decreased accuracy of 76%, which is obvious because we've eliminated many features, but now the specificity has increased to 45%, which indicates it's able to classify more bad instances correctly as bad. Sensitivity has decreased slightly to 89%. We'll now use grid search to perform hyperparameter tuning on this model as follows, to see if we can improve the performance further. The parameters of interest here include nTree, indicating the number of trees, node size, indicating the minimum size of terminal nodes, and mtry, indicating the number of variables sampled randomly at each split. We now get the best model from the grid search, perform predictions on the test data. Next, we evaluate its performance with this code snippet. We can make several observations from the output. Performance has improved very negligibly, as the overall accuracy remains the same at 76%, and specificity at 46%. Sensitivity has increased slightly to 90% from 89%. We now plot some performance curves for this model. We get this plot. Let's check the AUC now. We get it as 0.76. From the plot, we can deduce that this AUC is much better than the red baseline AUC of 0.5. Or to be more specific in this case, artificial neural networks is a family of machine learning models whose concepts are based on the working of biological neural networks, just like our nervous system. Neural networks have been there for a long time, but recently there's been an upsurge of interest in building highly intelligent systems using deep learning and artificial intelligence. Deep learning makes use of deep neural networks, which are essentially neural networks with a huge number of hidden layers between the input and output layers. A neural network depends on several neurons or nodes, and the pattern of interconnection between them. We'll start by loading the necessary dependencies. Then we transform the data as we did earlier. We'll now have to do some feature value encoding, similar to what we did when we did AUC optimization for SVM. To refresh your memory, you can run this code snippet. Once we have our data ready, we'll build our initial neural network model using all the features. The code snippet might ask you to install the nnet package if you do not have it installed, so just select the option when it asks you and it will install it automatically. Remember, it's an iterative process, so the model building might take some time. Once the model converges, you can view the model details using the print nn.model command, which will show you several iteration results with different size and decay options. And you'll see that it does hyperparameter tuning internally itself to try and get the best model. We now perform predictions on the test data and evaluate the model performance. You can observe from the output that our model has an accuracy of 71%, which is quite good. It's predicting bad ratings as bad quite well, which is evident from the specificity, which is 38%. And as usual, sensitivity is good at 85%. We'll now plot the features of importance for neural network-based models. This gives us the plot that ranks the variables according to their importance. We select some of the most important features from the plot and build our next model using these lines. It takes some time, so sit back and relax a while till then. We next perform predictions on the test data and evaluate the model performance. This gives us the confusion matrix with various metrics of our interest. We observe that the accuracy has increased slightly to 71% and sensitivity has now increased to 87%, at the cost of specificity, which has dropped here to 35%. You can check the hyperparameter tuning, which is done internally. The plot shows the accuracy of the various models, with different numbers of nodes in the hidden layer and the weight decay. Based on our requirement that the bank make minimum losses, we select the best model as the initial neural network model that was built, since it has an accuracy similar to the new model, and its specificity is much higher, which is extremely important. We now plot some performance curves for the best model. We get the plot. Now to find the AUC, we run these two lines. We get AUC as 0.70. Even the plot shows that AUC is 0.70, which is quite good, and performs a lot better than the baseline denoted in red. This concludes our predictive modelling session. We'll wrap it up with model selection and comparisons. Our test data has 130 instances of customers with bad credit rating 0 and 270 or 277 customers with good credit rating 1. If you remember, earlier we talked about using domain knowledge and business requirements after doing modelling to interpret the results and make decisions. Right now, our decision is to choose the best model to maximise profits and minimise losses for the German bank. Let's consider the following conditions. If we incorrectly predict a customer with bad credit rating as good, the bank will end up losing the whole credit amount lent to him since he will default on the payment, and so loss is 100%, which can be denoted as -1 for our ease of calculation. If we correctly predict a customer with bad credit rating as bad, we correctly deny him a credit loan, and so there is neither any loss nor any profit. If we correctly predict a customer with good credit rating as good, we correctly give him the credit loan. Assuming the bank has an interest rate on the sum of money lent, let's assume the profit is 30% from the interest money that is paid back monthly by the customer. Therefore, profit is denoted as 30% or plus 0.3 for our ease of calculation. If we incorrectly predict a customer with good credit rating as bad, we incorrectly deny him the credit loan, but there is neither any profit nor any loss involved in this case. Keeping these conditions in mind, we'll make a comparison table for the various models, including some of the metrics we had calculated earlier for the best model for each machine learning algorithm. Remember that considering all the model performance metrics and business requirements, there is no one model that is best among them all. Each model has its own set of good performance points, which is evident in the following analysis. The cells highlighted in the table show the best performance for that particular metric. As we mentioned earlier, there is no best model, and we've listed down the models that have performed best against this metric. Considering the total overall gain, Decision Tree seems to be the model of choice. However, this is assuming that the credit loan amount requested is constant per customer. This analysis is a bit complex. If you remember, there is a credit.amount feature which specifies the credit amount requested by the customer. Since we already have the customer numbers in the training data, we can aggregate the rated customers with the requested amount and sum up the ones for which losses and profits are incurred, and then we'll get the total gain for the bank for each method. It has been innovatively used in certain circumstances, unimaginable before, such as finding people in times of natural calamities, such as earthquakes or typhoons. The asymmetric relationship and high-speed information exchange aid in making Twitter such a dynamic entity. If we closely analyze and study the data and dynamics of this social network, we can uncover many insights. Let's apply some data science to tweets. The process of data mining, analogous to the mining of minerals, involves a few steps to be performed. Firstly, data cleansing to remove noise and unwanted data. Then, data transformation to transform the data into relevant form for analysis. After that, data or pattern evaluation to uncover interesting insights. Lastly, data presentation to visualize knowledge in a useful form. If we take a minute to understand these steps, we can see that we used exactly the same process across our projects. For the detailed information about data mining social networks and mining social network data, you can refer to reference material provided along with the code bundle. Let's be specific and talk about the data contained in a tweet. A sample tweet looks something like this. A tweet, as we all know, is a 140-character message. Since the message is generated by a user, usually, the actual message may be of a different length, language, or it may contain images, links, videos, and more. Thus, a tweet is a structured data point which contains the handle of the user, the name of the user, the message, the number of likes, and the number of retweets. A tweet may also contain hashtags, hyperlinks, images, and videos embedded within the message. As we'll see in the coming sections, a tweet contains tons of metadata, data about the data, apart from the attributes discussed previously. This much information from a single tweet, coupled with millions of users tweeting frantically every second across the globe, presents a huge amount of data with interesting patterns waiting to be discovered. Thus, the mining of data from a social network involves understanding the structure of the data point, the underlying philosophy or use of the social network, the velocity and volume of the data being generated, along with the thinking cap of a data scientist. So far in this course, we've analysed data and made use of line graphs, bar graphs, histograms, and scatter plots to uncover and present insights. To enable easy consumption of information or knowledge, we take the help of different visualizations, such as line graphs, bar graphs, pie charts, histograms, and other details. Some unconventional yet widely used visualizations are word clouds, tree maps, and pixel-oriented maps. To learn these types of visualization in more detail, you can refer to the reference material provided along with the code bundle. Twitter is as much a delight for people using Twitter to tweet, as it is for data scientists. The APIs and the documentation are well updated and easy to use. Let us get started with the APIs. Twitter has one of the easiest yet most powerful set of APIs available of any social network out there. These APIs have been used by Twitter itself and data scientists to understand the dynamics of the Twitter world. Twitter APIs make use of 4 different objects, namely tweet objects, user objects, Twitter entities, and Twitter extended entities. These objects from the Twitter APIs have been explained at length on this website, as you can see here. We urge viewers to go through it to understand the objects and APIs even better. Twitter has libraries available in all major programming languages and platforms. We'll be making use of twit_r, that is Twitter's library for R. Now that we have enough background information about Twitter and its API objects, let's get our hands dirty. The first step when starting to use the APIs is to inform Twitter about your application. Twitter uses the standard Open Authentication, OAuth, protocol for authorizing a third-party app. OAuth uses an application's consumer key, consumer secret, access token, and access token secret to allow it to use APIs and data of the connected service. Let's perform some quick steps to set us up for the game. Firstly, we'll go to Twitter's Application Management Console at this URL and log in with your credentials, or create an account if you don't have one. As you can see, I've already logged in. Then we'll click on Create New App and fill in all the details for the app's name, website, and so on. For our purposes, we'll name our app Twitter Analysis RMRE App. Add description and provide the URL. For callback URL, we'll use this URL to point back to your local system. You may choose any other port number as well. Click on the checkbox and accept the terms and conditions. Click on Create your Twitter application to complete the process. Congratulations, your app is created and registered with Twitter. But before we can use it, there's one more piece to do. We need to create access tokens, and to do that, we need to perform certain steps. For that, we'll go to the Link Keys and Access Tokens on the Twitter app's details page. Then scroll down and click on Create My Access Token to generate an access token for your profile. We'll be using the same application for this as well as in further videos. So make a note of the consumer key, access token, secret. We'll need these in our application. Now that we have everything ready at Twitter's end, let us set things up at ours end as well. Before we start playing with the data from Twitter, the first step would be to connect and authenticate ourselves through the app we just created using R. We'll make use of R's twit_r and load it using the library function. This library or client allows us to use Twitter's web APIs through R. As you can see in this block of code, that we've specified our app's credentials, that is consumer secret, consumer keys and access tokens secret. Then we'll set our credentials by using the setup Twitter OAuth function to connect to Twitter using our app's credentials, keys and access tokens. Upon executing this code, it'll prompt you to use a local file to cache credentials or not. For now, we'll say no to it. Congratulations, you're now connected to the ocean of tweets. Now that we're connected to Twitter using R, it's time to extract some latest tweets and analyze what we got. To extract tweets, we'll use the handle for Twitter's account 001, Twitter's founder and first user, Jack Dorsey, @Jack. First, we'll define the Twitter user using the getUser method. Now let's extract Jack's latest tweets with this line of code, which will extract the latest 300 tweets from him. Lastly, we'll print the tweets. As you can see, that the output contains text with unprintable characters and URLs due to Twitter's content-rich data. We'll look at the metadata of a tweet in a bit. Further, to see the attributes and functions available to analyze and manipulate each tweet, we'll use the getClass method. So first, we'll get tweet attributes. In the console, you can see all the tweet class fields. Then we'll get the retweets count with this line of code. Also, we'll print the favorite count. As you can see, it returns the value as 88. Awesome! So, using this data, we'll be uncovering some interesting insights while using different functions and utilities from Twitter and other R packages. Here we'll use the same app and its credentials to connect and tap into Twitter for data. Apart from connecting to Twitter, let's use library function to load some more packages. The results look something like this. As we can see, we get about 14 terms with a minimum occurrence of 10. If you look carefully, the terms we saw with frequencies of at least 15 also appear in this list, and rightly so. Now that we're certain that there are terms or words with occurrences of more than 10, let's create a data frame and plot the term versus their frequencies, as we decided previously. First, we'll use the row sums function to calculate the total occurrence of each term or word. Then we'll pick a subset of terms which have more than 10 occurrences. Now let's create a data frame from subset of terms. After that, we'll create a data frame with all terms. Next, we'll add a few lines of code to sort by subset data frame frequency. Lastly, we'll plot words by frequency from subset data frame with this code snippet. It will generate this frequency graph. Upon analysing the preceding graph, we can quickly get some interesting points. The words goals, change, health, habits, and tips feature in the top 10. Strange set, yet interesting. More on this in a bit. Health features high in the list, but doesn't make it to the top 3. So it seems like health is on the cards, but not very high. This is the same for poor and New Year. Most of the words in this list are positive in essence. Words such as goals, change, New Year, habits, and so on all point to the upbeat mood, while taking up New Year's resolutions. Though this graph gives us quite a lot of information regarding the words and their frequencies in a nice layout, it still doesn't show us the full picture. Remember that we crafted a subset of items from our dataset before generating this graph? We did that on purpose. Otherwise the graph would have become too long and words with lesser frequencies would clutter the whole thing. Another point which this graph misses out is the relative difference in the frequencies. If our aim is to see the relative difference between the frequencies, we need a different visualization altogether. Here comes word cloud to the rescue. Using the word cloud library, we can easily generate word clouds from a data frame using a one-liner. So we'll implement it by entering this line of code. The word cloud using the complete data frame looks something like this. This word cloud renders words in decreasing order of frequency. The size of each word emphasizes its frequency. You can play around with the word cloud function to generate some interesting visualizations or even art. A lot of words appear in the preceding graphs, but isn't it rather interesting to see the word trillionaire pop up in the top 10? What could be the reason for it? Was it a spam post by a bot or a tweet by some celebrity that went viral, or something completely different altogether? Let's check out the top tweet in this list and see if it contains the word living. For that, we'll run this line of code. It will return the output in these 2 lines. It turns out that our hunch was right. It was a New Year resolution tweet about healthy living article. Fitness is important to most of us. Activities such as exercising or hitting the gym see a surge during the initial months and weeks of the year. Let's see how health conscious our friends on Twitter are. Since a lot of words such as health, diet, fitness, gym and so on point towards a healthy lifestyle, let us try and find the words associated with the word fitness itself. Find a socks is a handy function which helps us find words from a term document matrix that have at least a specified level of correlation to a given word. For that, we'll enter this line of code. The words most closely correlated to the word fitness, as you can see here in the console window. Then we'll use the output from this function to prepare a term association correlation graph using ggplot. The same data is more readable in graphical format. In this graph you can see the terms such as nutrition, exercise, food and so on prove our point that people are as concerned about health as we are. It's interesting to note the occurrence of the term editor at work in this list. It looks like work is catching up with other techniques of staying fit in this year, so there's resolution on the list too. Proceeding with popular devices. So far we've dealt with the visible components of a tweet, such as text, retweet counts and so on, and we were able to extract many interesting insights. Let us take our precision tools and dig deeper into our data. To get this information, we'll make use of the attribute tweetSource from our data frame trendingtweets.df. First, let's get the column of the trending tweets df. As you can see, we'll make use of tweet source attribute from this data frame. Then, we'll use a subset of a data frame trending tweets.df based on retweet counts for the sake of clarity. So we'll enter a code to source by retweet count. Lastly, we'll use ggplot again to visualize our results. As you can see, this plot is our result. Without a doubt, the web is the most preferred device, followed by Android and the iPhone. It's interesting to see that people use the website to retweet more than the iPad and other devices. Windows Phone clearly has some serious issues to tackle here. Inferences such as these and many more require a bit more digging than this, but all of this has a lot of knowledge and potential that could be used by managements, UX teams and so on to improve and change things around. Awesome! Let's take this opportunity to understand hierarchical clustering before we apply it to our data. Hierarchical clustering, like any other clustering algorithm, helps us group similar items together. The exact details for this algorithm in general can be explained with 3 steps that we'll discuss next. Initialize. This is the first step where each element is assigned to a cluster of its own. A distance or similarity measure is decided at this step. Merge. During this step, depending on the distance or similarity measure chosen, the closest pair of clusters are identified and merged into a single cluster. This step results in 1 fewer clusters than the total clusters so far. Last step is compute or recompute. We compute or recompute distances or similarities between the new clusters formed in the merge step and the existing clusters. To perform hierarchical clustering, we first treat our dataset to remove sparse items for the sake of clarity. For this, the remove sparse items function will help us remove rows of data that have sparsity below a certain specified limit. Then we'll convert it into the matrix. After that, we'll calculate the distance using dist function. And create cluster using the hclust utility. The output of this utility is directly plottable. So let's plot the output. The output dendrogram is generated under the Plot tab, and it's amazingly simple to understand. If you observe the second cluster from right, it contains terms, settlement, promotion, commitment, and so on. Mapping back to the top retweeted tweet, all these terms are mentioned in that single tweet, and our algorithm has rightly clustered them together. Smart, isn't it? As a small exercise, observe other clusters and see how the terms occur in the tweets that contain them. One important observation to make here is that the dendrogram correctly maps all frequent terms under a single root, which reaffirms that all these terms point to our central theme of resolutions. Further, we'll move on to topic modeling. Topic modeling is a process of discovering patterns in a corpus of unlabeled text that represents the gist of the corpus. A topic itself may be described as a group of words that occur together to describe a large body of text. Your results may vary due to the dynamic nature of Twitter. You may observe a difference in the outcomes across other examples in this section as well. We urge you to be creative and try out other trending topics while working through examples from this section. For the purpose of topic modeling, we shall use a new set of tweets. The International Space Station, ISS, has multiple Twitter handles, and one of them is @ISS_research, which particularly caters to research-related tweets from the ISS. Let's explore what @ISS_research is up to these days by analysing the tweets from its timeline. We'll analyse these tweets to identify the underlying topics of research at the ISS. For this purpose, we'll use the same process to extract tweets and perform transformations and cleanup as we've done before. So first, we'll set the user handle using getUser function. Then we'll enter a line of code to extract 1000 tweets from ISS research tweets. Post that, we'll transform it to data frame. We'll perform the transformation with this code snippet. Now let's transform it to document term matrix. We need to note that this will prepare a document term matrix, unlike last time where we prepared a term document matrix. Once we have tweaked in the required format, the LDA utility from the Topic Models package will help us uncover the hidden topics and patterns. The LDA utility requires the number of topics as input along with the document term matrix. We'll try 8 topics for now. Then we'll enter a code to find the first 6 terms of every topic. Enter a line of code to concatenate the terms. Here we've used LDA to extract 6 terms for each of the 8 topics. This is the list of topics generated using LDA. A visual representation would be easy to understand. We'll make use of qplot to quickly plot the topics across time on an area chart. Let's execute the code for the first topic identified for every tweet. Plot the topics across time by executing this code snippet. The generated chart looks like this, as you can see here. Let's now analyze the outputs. The list of terms per topic generated by LDA seems to give us a nice insight into the kind of work and research going on at the ISS. Terms such as atom, crew, billion, Cygnus, and so on tell us about the main areas of research. The qplot output adds the time dimension to our plain list of topics. Analysing topics across the time dimension helps us understand when a particular research topic was discussed, or when something amazing was announced. Topic 2 in the list, or the 5th one from the top in the graph legend, comprises the word Cygnus. A quick look on Twitter and news websites confirms that the news broke by tweet 14th of May 2018. Close enough. If you want to experiment with the look and feel of the plot, we can do it by modifying the previously used code and re-executing it. With a slight tweak in the code, we can view the colourful plot. So we finally learnt about topic modelling using LDA on data from the ISS and found what amazing things scientists and astronauts are doing up there in outer space. Awesome! Sentiment analysis aims to identify the positive, negative or neutral opinion, sentiment or attitude of the speaker using said techniques. Sentiment analysis finds its application in areas from commerce to service domains across the world. Let's look at the key concepts of sentiment analysis. We'll now examine the key terms and concepts related to sentiment analysis. These terms and concepts will help us formalize our discussions in the coming sections. First key term is subjectivity. Opinions or sentiments are one's own expressions of views and beliefs. Furthermore, subjectivity expresses our sentiments about entities such as products, people, governments, and so on. Next is sentiment polarity. It involved placing the text sentiment on a continuous or discrete scale of polarities, thus defining the degree of positivity. The sentiment polarity classification may deal with a different set of classes depending on the context. Another term is opinion summarization. Opinion classification or sentiment extraction from a piece of text is an important task in the process of sentiment analysis. This is often followed by a summarization of sentiments. It may involve the use of visualizations to infer the overall sentiment. Moving on to feature extraction. As we've seen across the chapters, feature identification and extraction is what makes or breaks a machine learning algorithm. It's the most important factor after the data itself. Let's look at some of the feature sets utilized in solving the problem of sentiment analysis. TF-IDF. In the context of TF-IDF, a piece of text is represented as a feature vector, containing words as its constituents. TF-IDF is given as this equation, where TF, T, D, is a term frequency of term T in document D. IDF, T, D, is the inverse document frequency for term T in document set D. Next is n-grams. The n-gram-based modelling techniques find their roots in information theory, where the likelihood of the next character or word is based upon the n previous terms. Parts of speech, POS, POS are rules of language which are used to create sentences, paragraphs and documents. In its simplest form, adjectives are usually pretty good indicators of subjectivity. Not always, though. In the case of sentiment analysis, negation plays an important role. For example, sentences such as "I like oranges" and "I don't like oranges" differ only in the word "don't", but the negation term flips the polarity of sentences to opposite classes, positive and negative respectively. Topic-specific features. Topic plays an important role in setting the context. Since sentiment analysis is about the speaker's opinion, the subjectivity is influenced by the topic being discussed. Let's proceed with approaches. Now that we have a basic understanding of the key concepts from the world of sentiment analysis, let's look at different approaches for tackling this problem. Sentiment analysis is mostly performed at the two levels of abstraction, such as document and sentence level. Document level. At this level of abstraction, the task is to analyze a given document to determine whether its overall sentiment is positive or negative, or neutral in certain cases. Sentence level. Sentence level analysis is a more granular form of sentiment analysis. The level of granularity counters the fact that not all sentences in a document are subjective. Pretty much like other machine learning techniques, sentiment analysis can also be tackled using supervised and unsupervised methods. Supervised learning approaches for sentiment analysis have seen a boost, both in terms of systems utilizing these techniques, as well as the overall performance of such systems, due to the availability of labeled datasets. Unsupervised algorithms for sentiment analysis usually begin with building or learning a sentiment lexicon. Now that we're equipped with the key terms and concepts from the world of sentiment analysis, let's put our theory to the test. Polarity analysis involved the scoring and aggregation of sentiment polarity, using a labelled list of positive and negative words. And classification-based analysis will make use of R's rich libraries to perform classification based on labelled tweets available for public usage. We'll also discuss their performance and accuracy. R has a very robust library for the extraction and manipulation of information from Twitter called twit-r. Before we begin our analysis, let us first restructure our existing code and write some helper functions, which will come in handy later on. As we know, the data from Twitter can be extracted using search terms or from a user's timeline. Let's create two helper functions that will help us do exactly the same tasks in a reusable fashion. For that, first we'll create a function to extract search tweets with this code snippet. Then we'll create another function to extract timeline tweets. The function extract tweets takes the search term and number of tweets to be extracted as inputs and returns data in a data frame with the text converted to UTF-8 encoding. Similarly, the function extract timeline tweets takes the username and number of tweets as inputs and returns data in a data frame with the text converted to UTF-8 encoding. Therefore, these two functions will help us to extract tweets multiple times without rewriting the same lines of code again and again. Continuing with the same theme, we'll write another helper function to clean and transform our dataset. As we saw in the previous section, R's TM library provides us with various utility functions to quickly clean and transform text corpus. We'll do that by adding and executing this block of code. Here, we'll make use of tmmap to transform our tweets. In addition to the usual transformations, such as stop word removal, change to lowercase, punctuation removal, and so on, the function transform tweets tokenizes each tweet at a word level and attaches the list of words in each tweet to the object. Also, the function returns the transformed tweets in a data frame for further manipulation. Let's run the code. Moving on to polarity analysis. Polarity, as discussed in the section Key Concepts, is the positive, negative, or neutral classification of the piece of text in consideration. The class labels may change depending on the context, liked versus disliked, or favourable versus unfavourable. Polarity may also have a degree attached to it, which places the analysed text on a continuous or discrete scale of polarities, say from -5 to 5. This degree of polarity helps us to analyse the extent or degree of positivity or negativity in the text. The simple and easy to code algorithm steps are represented diagrammatically. 1. Extract tweets based on selected search terms or Twitter handles. 2. Clean and transform tweets into a suitable format for ease of analysis. Tokenize tweets into a constituent list of words. 3. Load the list of positive and negative words to be used for polar word identification. 4. For each tweet, count the number of positive and negative words that match the list of positive and negative words obtained in the preceding step 3. 5. Assign a polarity score to each tweet based on the difference between positive and negative matches in the preceding step. Once each tweet in the data set has been scored, we may aggregate the scores to understand the overall sentiment distribution related to the search terms or Twitter handle. Positive values define a positive sentiment. Larger numbers denote a greater degree of positivity, and similarly for negative sentiments. A neutral stance is represented by a score of 0. Let's consider a scenario where one is tasked with analysing the effectiveness of and public opinion related to such an initiative. To analyse public opinion, which changes dynamically over time, Twitter would be a good choice. So, to analyse sentiments for the Make in India initiative, let us analyse some tweets. Once our dataset is ready and in a consumable format, we load the precompiled list of positive and negative words. The list is available at this web link. Navigating back to RStudio, first we'll write a reusable analyze trend sentiments function, which takes the search term and number of tweets to be extracted as inputs. It makes the use of functions extract tweets and transform tweets to get the job done. Let's execute this code snippet. Then we'll use the function analyze trend sentiments to get a data frame consisting of tweets scored using a precompiled list of polar words. We'll use twitr, tm, stringr and ggplot2 libraries as well, which we load using the library function. After that, we'll define consumer secret, consumer key, access token, and access token secret with these few lines of code. Let's make connection with a Twitter account. Now as we have two files, that is positiveword.txt and negativeword.txt in the code bundle. So, we'll use that as a list of positive and negative words from Opinion Lexicon. You can see that it reads 206 items in positive words and 483 items in the negative words.txt file. Next, we'll extract 1500 tweets on the given topic. It may take some time to extract. Once it's done, we'll plot the aggregated scores on a histogram. As you can see, we generated a histogram of aggregated scores. The visualization looks like this. The histogram is easy to interpret. It shows the tweets distributed across a polarity scale on the x-axis and frequency of tweets on the y-axis. The results show a normal distribution with a general tilt towards the positive side. It seems the initiative is getting a positive response from its audience. Now let's analyse world leaders' sentiments. Twitter has caught the frenzy of celebrities and politicians alike. As a quick exercise, try analysing tweets from the Twitter handles of world leaders such as Narendra Modi, PMO India and PMO India RC with 3 lines of code. Again, it may take some time. Once it's done, we'll bind these times with this code. To visualise the plot by executing this code snippet. Here in this plot, we can see 3 sentiments related to 3 different timelines. Awesome! Note, for this section, we'll concentrate only on the positive and negative polarities, but the approach is generic enough to be easily extended to include the neutral polarity as well. Since this is a supervised learning approach, we require labelled data for training and testing the performance of our algorithms. For the purpose of this section, we'll utilise a labelled dataset from this web link. It contains tweets labelled as 0, 2 and 4 for negative, neutral and positive sentiments respectively. Let's open the file and see what attribute it contains. There are various attributes such as tweet ID, date, search query, username and the tweet text, apart from the sentiment label. For our case, we'll be considering only the tweet text and its corresponding label. Before we get into the algorithm-specific details, let's look into the labelled dataset and perform the initial steps of collecting and transforming our data into the required forms. So, we'll make use of libraries, such as Caret and R text tools for these steps. Let's navigate to the R session and load the required libraries and matrix calculations. Then we'll load the dataset with these 2 lines of code. As you can see, we already have the labeled tweets.csv file available in a working directory. We'll execute the code and move ahead. As previously mentioned, the dataset contains polarities labelled as 0, 2 and 4 for negative, neutral and positive. Next, we'll apply a quick transformation to change the labels to positive and negative with this block of code. Once the polarities have been transformed into intelligible names, we'll filter out the rows of data containing neutral sentiments. Also, we'll keep only the columns for polarity and tweet text, and remove the rest. So, to select only the required column, we'll type this line of code. Now we'll extract only positive and negative labelled tweets. The tweets object is now available as a matrix, with each row representing a tweet, and with columns referring to polarity and tweet text. Before we transform this matrix into the formats required by the classification algorithms, we need to split our data into training and testing datasets. For that, we'll execute these few lines of code. Since both the training and testing datasets should contain a good enough distribution of samples of all classes for the purpose of our training and testing, we use the create data partition function available from the caret package. For our use case, we'll split our data into 70 by 30 training and testing datasets. Next, we'll perform a quick check to see how our data is split across the positive and negative classes in our original dataset, the training and testing datasets using the prop function. First, we'll verify the split of original dataset. On executing, you'll see the result simultaneously in the console window. Then we'll check for the training dataset and testing dataset. As we can see, Create Data Partition has done a nice job of maintaining a similar sentiment distribution across the training and testing datasets. Next in line of transformations is the document term matrix transformation. As we've seen in the previous section, a document term matrix performs a given dataset into rows representing the documents and columns of terms, words or sentences. Unlike the previous section, where we used the TM library's document term matrix function for transformation and applied various transformations using TM-map, for the current use case, we'll use the create matrix function from the R text tools library. We'll implement it with this code snippet. This function is an abstraction over TM's corresponding functions. We'll also assign weights to each of the terms using TF-IDF as our feature. The create matrix method also helps us take care of splitting sentences into words, stop words and number removal, and stemming them as well. Similarly, we do it for test.dt matrix as well. To calculate the size of the rows, we'll enter and execute this line of code. Now that we have both the training and testing datasets in the document term matrix format, we can proceed towards the classification algorithms and let our machines learn and build sentiment classifiers. Further moving on to support vector machines. Support vector machines, or SVM as they're commonly known, are one of the most versatile classes of supervised learning algorithms for classification. An SVM builds a model in such a way that the data points belonging to different classes are separated by a clear gap. Since our current use case for sentiment analysis is also a binary, positive and negative, classification problem, SVM helps us build a model using the training dataset, which separates tweets into positive and negative sentiment classes respectively. We'll use E1071 library's SVM function to build a sentiment classifier. We start off with the default values for the SVM classifier available from the library, to finally arrive at the best classifier. Let's build the sentiment classifier using the default values. Now we'll print the initial model details using the summary function. This is the summary generated in the console window. After that, we'll enter the code and calculate the predictions. Also get the true labels with the next line of the code. The following snippet of code builds a sentiment classifier using the default values, and then prints a confusion matrix along with other statistics for evaluation, as shown in the following code snippet. Lastly, we'll create the confusion matrix for the same. The generated confusion matrix shows that the classifier has just 50% accuracy, which is as bad as a coin toss, with no predictions for negative sentiments whatsoever. It seems like the classifier couldn't infer or learn much from the training dataset. To build a better performing model, we'll now go under the hood and tweak some parameters by executing this block of code, where we'll run the grid search and observe the tuning result. The SVM implementation from E1071 provides us with a wonderful utility called tune to obtain the optimized values of hyperparameters using a grid search over the given parameter ranges. This is the parameter tuning results in optimized values for hyperparameters cost and gamma as 10 and 0.01 respectively. This is the parameter tuning result. As you can see, this is a generated plot that confirms the same, that the darkest region corresponds to best values. Further, we'll use the best model to predict and prepare a confusion matrix with these lines of code. This is the generated result of the confusion matrix. It shows the predictions from a much improved model. From a mere 50% accuracy to a comfortable 71% and above is a good leap. Let's check the ROC curves for this model to confirm the accuracy is indeed good enough. To prepare the ROC curves, we'll reuse our utility script performanceplotutils.r from the previous section, and pass the predictions from the optimized model to it. For that, we'll implement this code snippet. Great! As you can see, the ROC curves generated successfully. Now let's calculate the AUC value with these lines of code. So, the ROC curves also conform to a well-learned model with the AUC of 0.8085. We can therefore use this model to classify tweets into positive or negative classes. Next, proceeding with ensemble methods. Ensemble of classifiers is defined as a set of classifiers whose outputs are combined in some way to classify new examples. The main discovery in the field of machine learning-based ensembles is that ensembles perform much better than the individual classifiers. A necessary and sufficient condition for ensembles to be better than their constituents is that they should be accurate and diverse. A classifier is termed accurate if its predictions are better than random guessing, see weak learners, while two classifiers are termed as diverse if they make different errors on the same data points. We can define a weak learner as a learner whose predictions and decisions are at least better than random guessing. Weak learners are also termed as base learners or meta-learners. For a better understanding about the concept of ensemble classifiers with diagrammatic representation, you can refer to the reference material provided along with the code bundle. There are various ways of constructing ensemble classifiers, or regressors, and boosting is one of them. The original algorithm for boosting was revised and termed as adder boost or adaptive boosting. This algorithm was practically implementable and empirically improved generalization performance. The algorithm can be mathematically presented as shown on this website. To learn more about boosting with another example, you can refer to the reference material provided along with the code bundle. Now that we have an overview of ensemble methods and boosting in general, let us use the boosting implementation available from the R text tools library in R to classify tweets as positive or negative. We'll reuse the training testing document term matrices train.dt matrix and test.dt matrix, and container objects train.container and test.container, which we created for the SVM-based classification. First, we'll build the train.container object with this code snippet. Similarly, we'll build the test.container object by executing this block of code. For building a classifier based on a boosting ensemble, our text tools provides an easy-to-use utility called train model. It uses logit boosting internally to build a classifier. We use 500 iterations for building our boosting ensemble. Then we'll enter the code to classify the matrix. Post that, we'll prepare a confusion matrix with this block of code to see how our classifier performs on the test dataset. Let's evaluate the confusion matrix. It shows that our boosting-based classifier works with an accuracy of 68%, which is fairly good given the fact that we did not perform any performance tuning. Compare this to the initial iteration of SVM, where we got a dismal accuracy of just over 50%. Plot the model evaluation matrix curve by executing this code snippet. You can see the generated output of boosting classifier. Lastly, we'll calculate the AUC value of the same. This is the successfully generated AUC value. As mentioned earlier, ensemble methods, specifically boosting, have improved generalization performance. That is, they help achieve a close to zero training errors without overfitting on the training data. To understand and evaluate our boosting classifier on these parameters, we'll use a model evaluation technique called cross-validation. So, cross-validation is used to evaluate the generalization performance of a model. It's also termed rotational estimation. It's a better measure to validate a model for generalization compared to residual methods. Cross-validation can be performed using the holdout method and k-fold cross-validation method. We can easily perform k-fold cross-validation on our boosting classifier using the cross-validate function. In general, 10-fold cross-validation is used. So, we'll use n as 10 and set the seed as 42. Then we'll use the cross-validation function with this line of code. On executing the code, it will start printing out the sample accuracy, so we'll enlarge the console window. This code has produced the cross-validation summary. The results show that the classifier has generalized well enough and has an overall mean accuracy of 97.8%. Boosting is one of the methods to construct ensemble classifiers based on weak learners. Methods such as bagging, Bayes, optimal classifier, bucketing and stacking are some of the variants with their own pros and cons. Awesome! That brings us to the end of this wonderful journey. I hope that you'll be able to use data analysis techniques in R and examples to apply machine learning to your own experiences. Data science is a journey of learning the knowns and exploring the unknown unknowns.